In my previous video, we learned how to establish a basic wireless communication between Arduino UNO and an ESP8266 NodeMCU using the nRF24L01 module by transmitting a simple hello world message. That was just the beginning. In this video, we are going to build a complete real-world wireless monitoring and control system. The Arduino UNO will read temperature and humidity from a DHT11 sensor and transmit the data wirelessly to the ESP8266. The ESP8266 will display the live sensor readings on an OLED display. But that's not all. I have connected a capacitive touch sensor to the ESP8266. By simply touching the sensor, we will wirelessly control a relay connected to the Arduino UNO. And to make the communication even more reliable, the Arduino will send the relay status back to the ESP8266. So the OLED display always shows the actual state of the relay along with the latest temperature and humidity reading. In other words, this is not just one-way communication anymore. It's complete two-way wireless communication system. So let's get started. For this project, we will need the following components: Arduino UNO, ESP8266 NodeMCU board, SSD1306 OLED display, nRF modules, DHT11 temperature and humidity sensor, capacitive touch sensor, relay module, light bulb, jumper wires, and breadboard. Before we start building this project, let's take a quick look at the nRF24L01 module and its breakout board. The nRF is a low-cost 2.4 GHz transceiver that allows two or more microcontrollers to communicate wirelessly. Since it is a transceiver, it can both transmit and receive data, making it ideal for applications such as wireless sensor networks, home automation, robotics, smart agriculture, industrial monitoring, and many other IoT projects. It communicates with microcontroller using the SPI protocol and offers reliable, low power, and long-range wireless communication. To improve the module stability, many makers use an nRF breakout board. The breakout board includes an onboard 3.3 volt voltage regulator and filter capacitors, which provide a clean and stable power supply to the nRF module. This helps prevent common issues such as communication failures, random disconnects, and the radio hardware not detected error. It also makes the module much easier to connect on a breadboard. In this project, I will be using the nRF24L01 with the breakout board to ensure a stable and reliable wireless communication between the Arduino UNO and the ESP8266 NodeMCU. Now let's install the nRF24L01 module into the breakout board. Carefully align the 8 pins of the nRF module with the socket on the breakout board, ensuring that the orientation is correct. Once the pins are properly aligned, gently press the module into the socket until it fits securely. Avoid using excessive force, as this may bend the pins or damage the module. With the nRF securely mounted, the breakout board will provide a stable power supply and a reliable connection, allowing us to proceed with wiring the transmitter and receiver circuits. Now let's build the transmitter circuit using the Arduino UNO. First, connect the nRF module to Arduino UNO. Connect the VCC pin to 3.3 volt pin or 5 volt if you are using the breakout adapter with an onboard regulator, and connect the ground pin to ground. Next, connect the CE pin to digital pin 9, CSN to digital pin 10, SCK to digital pin 13, MOSI to digital pin 11, MISO to digital pin 12. Now connect the DHT11 sensor. Connects its VCC pin to 5 volt, ground to ground, and data pin to digital pin 4 of the Arduino UNO. Finally, connect the relay module. Connect the VCC pin to 5 volt, ground to ground, and the N pin to digital pin 6. The relay can be connected to any external load according to your application requirements. With these connections complete, the transmitter circuit is ready to read sensor data, control the relay and communicate wirelessly with the ESP8266. Now let's build the receiver circuit using the ESP8266 NodeMCU. First, connect the nRF module to the ESP8266 NodeMCU. Connect the VCC pin to the 3.3 volt pin and the ground pin to ground. Then connect the CE pin to D4, CSN to D8, SCK to D5, MOSI to D7 and MISO to D6. Next, connect the SSD1306 OLED display. Connect the VCC pin to 3.3 volt, ground to ground, SDA to D2 and SCL to D1. Finally, connect the capacitive touch sensor. Connects its VCC pin to 3.3 volt, ground to ground and the out pin to D0 of the ESP8266 NodeMCU. With this connection complete, the receiver circuit is ready. The ESP8266 will continuously receive the temperature, humidity and relay status from the Arduino, displaying the information on the OLED screen, and wirelessly control the relay whenever the capacitive touch sensor is touched. First, install the RF24 library for the nRF module. The transmitter code begins by including the required libraries for SPI communication, the nRF24L01 module and the DHT11 sensor. An RF24 object is created by specifying the CE and CSN pins, and a DHT object is initialized to read the temperature and humidity values. Two different addresses are then defined, one for receiving command from the ESP8266 and another for sending sensor data back, allowing true two-way communication. A pegged packet structure is also created to transmit multiple values, including temperature, humidity, relay status, and button state in a single wireless packet, while ensuring the packet size remains same on both the Arduino UNO and the ESP8266. In the setup function, serial communication is initialized. The relay pin is configured as an output, and the DHT11 sensor is started. The program also displays the packet size to verify that both microcontrollers use the same data structure. The nRF24L01 module is then initialized, and several communication parameters such as transmission power, data rate, channel number, automatic acknowledgement, and retry count are configured to provide stable and reliable wireless communication. Finally, the Arduino UNO opens both the reading and writing pipes and enter the listening mode to wait for commands from the ESP8266. Inside the loop function, the Arduino reads the temperature and humidity from the DHT11 sensor every 2 seconds and stores the latest valid values. Whenever a wireless command is received from the ESP8266, the Arduino checks the received button state and turns the relay on or off accordingly. It then updates the packet with the latest temperature, humidity, relay status and packet ID before switching the nRF24L01 into transmit mode. The updated packet is sent back to the ESP8266 as feedback, allowing the receiver to display both the latest sensor reading and the actual relay status on the OLED display. This continuous exchange of data creates a reliable two-way wireless communication system between the Arduino UNO and the ESP8266. The receiver code begins by including the required libraries for the nRF24L01 module, OLED display and I2C communication. An RF24 object is created by specifying the CE and CSN pins, while an OLED display object is initialized with the screen dimension. Similarly to the transmitter, two different addresses are defined, one for sending commands to the Arduino UNO and another for receiving sensor data and relay status. A pegged packet structure is also created so that both the ESP8266 and Arduino UNO use the same data format for reliable communication. Inside the setup function, the capacitive touch sensor is configured as an input, and the packet size is displayed on the serial monitor to verify that it matches the Arduino UNO packet size. The OLED display is then initialized and cleared before use. Next, the nRF24L01 module is configured with the same communication setting as the transmitter, including transmission power, data rate, communication channel, automatic acknowledgement, and retry count. Finally, both the writing and reading pipes are opened, preparing the ESP8266 to send commands to the Arduino UNO and receiver sensor data in return. Inside the loop function, the ESP8266 continuously monitors the capacitive touch sensor. Whenever the sensor is touched, the program toggles the relay command between on and off. This command is then transmitted wirelessly to the Arduino UNO using the nRF24L01 module. After sending the command, the ESP8266 switches to receive mode and wait for replay from the Arduino UNO. The received packet contains the latest temperature, humidity and relay status, which are displayed on both the serial monitor and the OLED display. This continuous exchange of commands and feedback enables real-time two-way wireless communication, allowing the ESP8266 to remotely control the relay while simultaneously monitor the sensor data from the Arduino UNO. Let's test our complete two-way wireless communication system. First, I will power on the ESP8266 receiver. As you can see, there is no data on the OLED display. That's because the Arduino transmitter is currently turned off, so no wireless packets are being sent. Now let's power on the Arduino UNO transmitter. As soon as it starts running, it begins transmitting the live temperature and humidity reading through the nRF24L01 module. Immediately, the ESP8266 receives the data and you can see the temperature, humidity and relay status being displayed on the OLED screen in real time. This confirms that the wireless communication link between the two boards has been established successfully. Next, let's test the wireless relay control. I will simply bring my finger close to the capacitive touch sensor connected to the ESP8266. As you can see, the relay connected to the Arduino UNO turns on, which is indicated by the light switching on. At the same time, the Arduino sends the updated relay status back to the ESP8266, and the OLED display instantly updates to show the new relay state. I will repeat this several times and you can see that every touch successfully toggles the relay on and off, while the OLED continuously displays the correct feedback. This demonstrates true two-way wireless communication, where commands are sent in one direction and acknowledgements are received in other. Finally, let's verify the sensor reading. I will provide some heat to the DHT11 sensor connected to the Arduino transmitter. As the sensor detects the increased temperature, the updated temperature and humidity values are transmitted wirelessly to the ESP8266. You can see the reading on the OLED display, changing almost immediately, confirming that the system is continuously monitoring the environment and sending live data in real time. And that's it. We have successfully built a complete two-way wireless communication system using the nRF24L01 modules, an Arduino UNO and an ESP8266 NodeMCU. In this project, we wirelessly transmitted temperature and humidity data from a DHT11 sensor, displayed the reading on the OLED display, remotely controlled a relay using a capacitive touch sensor, and received a real-time relay status feedback from the Arduino. This demonstrates how the nRF24L01 can be used not only for wireless monitoring but also for reliable remote control applications. The best part is that this project can be easily expanded by adding more sensor, actuators or additional nRF24L01 nodes to build larger wireless sensor networks and smart automation system. I hope you found this tutorial helpful and learned something new. If you enjoyed this video, please give it a thumbs up. Subscribe to the channel and press the notification bell so you never miss upcoming Arduino, ESP8266, ESP32, robotics and IoT projects.